Check it out now, y'all.
NanoHub U, online instruction.
Okay, so this week we discussed two special type of sensors, amperometric sensors and cantilever sensors. You remember that there are basically three that we planned to discuss. One was in the previous module, it was all about potentiometric sensors, the various limits associated with potentiometric sensors, meaning screening, pH-based interference of the sensor surface. This week, primarily, we are thinking about amperometric sensors, which has slightly better selectivity, and cantilever sensors, which is mass-based. So I'll give you a few examples and hints because the solution manuals are all available, or so the solutions are all available to you, and so you should take a look. But let me just work out a few of the homework so that you know what to look for. So I'll have maybe two examples from the amperometric sensors and a few from the cantilever sensors, and then we'll be done. Now, amperometric sensors, of course, depends very sensitively on the various electrodes we have, and it's very important, you see, to get comfortable with the electrochemical potential associated with various types of sensors. So remember, there are two divisions, two classes. One is the spontaneous reaction, where the electrons essentially want to go from higher electrochemical potential to the lower electrochemical potential, oxidation potential. And in this case, for example, that's the case for the battery. And the first example in 4.1, we essentially wanted to explore that particular problem. Spontaneous reaction where the chemical energy is being converted into an electrical energy. Of course, you remember the Butler-Volmar and the other equations. There you had to apply a voltage before the reaction got initiated. So this example is not that. It is a spontaneous reaction. And so this particular example says that we have two electrodes. One is cadmium, and then another was antimony. So this could be side by side like this, immersed in the respective solution. And in the respective solution, cadmium 2 plus can immediately get into, cadmium or antimony 2 plus can get to an antimony. So these ion exchanges are possible. So the question that was which method metal will be cathode, which method metal will be anode, write the half reaction going on in the separate chamber. Remember, the cadmium electrode is in one chamber, the antimony electrode is in the other chamber, and we are asking that write down the reaction for this chamber, that's one half reaction, write down the reaction for this chamber, which is another half reaction, and that's the half reaction, and what is the electromotive force, net force for this particular cell. So that's the question being asked. And the solutions are relatively easy. You can look at the standard reduction potential. Reduction potential means that so when somebody is accepting electron, that means it is getting reduced. So therefore, in general, you see the cadmium would accept, it will donate its electron, right? It donates its electron, and antimony accepts it. And so this is the whole reaction, and therefore the half reaction will be that in here the cathode, in the cathode, for example, it will accept the electrons. So if you look at the lecture slides, you will see that the electron goes from the anode. After getting oxidized, it goes to the cathode, and there it deposits its electron. So this would be the half reaction associated with antimony. And cadmium, since it gives away electron, so therefore, and in the process gets oxidized, and so this would be the anode. It will be called an anode. And the corresponding EMF would be the difference of these two potentials. So you have in one case 0.136 for the cathode. In this particular case, it is less negative, and then correspondingly minus 0.403. But we are looking at the difference. So once you take the difference, we'll have about 0.267 volts for the electromotive source. So the bottom line is that you always look at this reaction, look at the big table, which has the list of all the reduction potentials. In the chemistry book, you will find you will always have to be a little careful whether it's the oxidation potential or reduction potential. And once you have sort of looked up from the handbooks or from Google these respective numbers, then you can decide that which one is anode and which one is cathode, which one wants to accept electron and which one wants to donate electron, right? So this is something, there are various sources from which you can get more insight into this problem. All right. The other problem, which is 4.3, was associated with current passing through an electrode of complex geometry. And you remember that when the redox reactions were going on between one electrode and the next, the important point was that between two electrodes, for example, the important point was that we got CDSs in this expression for arbitrary geometry. If you have a cylinder, then you have to write the corresponding diffusion equivalent capacitance associated with the cylinders. If you have two spheres, then you have to write the corresponding diffusion equivalent capacitance of the two spheres. And what is very important to check that I did all the derivations for planar electrode and then simply generalized to in here. But in this expression, if you put back the planar electrode expression, you should get this back and make sure that that happens. And that's what it is done. You see, in case of CDSs, for the planar electrode, you assume the two electrodes have the same size. So AB is equal to AA, that they are equal. And also, and so therefore you have to put, and also the CDSs is given by epsilon naught A over D. Or in this particular case, epsilon is replaced by the diffusion coefficient D. So you put this in, put it in here, and you will see that immediately you get back the expression that we had before, AD over W here, and another D over W, because there is a A here. The A will cancel the corresponding A in the CDSs, and so therefore you'll have a D over W in this particular case. So in general, these equations therefore are completely equivalent, and that gives us the confidence. Of course, you saw many examples that we did in the lecture itself where this equivalence was shown to be correct. Okay, so on amperometric sensors, there are one or two other examples that you should be checking out. So one example for the cantilever sensors was that whether you can weigh a virus. Now that was something very interesting because, of course, as things have gotten small, the cantilevers have gotten very, very small. Many people have reported that they can detect virus. What I want to emphasize today through this example is that you have to be a little careful as you look at those papers, read those papers. So let's say a typical virus weighs about tens of attogram. Attogram is 10 to the power minus 18 gram. Attogram. And if you have a silicon cantilever beam with a Young's modulus, let's say of 150, density of 2300, couple of microns long and wide, and relatively thin, let's say 25-30 nanometer, then let's see whether we can detect this type of a typical virus. Because that would be good, because most of the viruses have this type of range. But there are other viruses which are considerably bigger, which are rare, but considerably bigger. And these viruses are, for example, are about 1,000 times bigger. So 10 femtogram, whereas typical viruses are 10 attogram. And let's see whether we can calculate the corresponding frequency shift. Now you remember, depending on the support of the cantilever, we'll have different types of alpha 1 and alpha 2 value when you look at the formula. So these are already given, so we don't have to worry about them. So let's see how much change would you expect in both cases. So the formula that we will be working with is delta F is delta M over 2M naught multiplied by F naught. You have omega naught is equal to square root of Km. Take log on both sides and take a differential. That will give you this formula. Of course, this formula completely neglects the delta K variation, right? There's no delta K over K naught in here. Why not? Because you see, delta K has to change the spring constant, like a starch, right? Like a starch, it has to stiffen the beam itself before delta K, and then you have to account for delta K. And that stiffening requires that you have many biomolecules sort of cross-linked with each other, making sure that there is this bending is more difficult, let's say. But when you have a single virus biomolecule, single one, in that case there is no delta K, because it's not cannot change on its own, change the stiffness. And so there is no delta K here. Of course, you can calculate the mass, is the density, WLH is, the volume, spring constants you already know, and this has been said to be alpha 2 is equal to 1. And then there is this corresponding value for I, let's say. Now, if you calculate the whole thing, you put it in, put this value of M naught in here, put this value of, put these values, and correspondingly for F naught, you will have to take this value of K naught from here and put it in there, and then you'll get some formula, which is good. Delta F is directly proportional to delta M, so you should be able to directly see the mass, the inertial mass, and of course the longer, so you want a relatively small length and relatively small width. You remember this is a micrometer size if you want to see a larger delta F. So the interesting thing is that for normal virus, if you put all those numbers together, you'll only have 120 hertz shift. Do you remember what is the typical resonance frequency? Couple of megahertz. And so if you have 100 hertz shift for typical viruses, that will be essentially be undetectable, especially when you have noise limit. So I think to this day still, even with nanoscale sensors, a normal virus, a typical virus will be difficult to detect by cantilever sensors. So what is it when people say that they can detect viruses? Well, they are talking about this larger viruses. It is 1,000 times heavier, and so therefore this is 1,000 times big. Delta M is 1,000 times big, and so therefore it's about 120 kilohertz, right? Or 0.12 megahertz shift. That is something you can easily detect. And so therefore larger viruses are possible, but day-to-day viruses are difficult to detect. The only way you can do the day-to-day viruses is to use another, like a tag, a heavier tag with it, so that when this little molecule along with the tag, they come together and bind to the sensor surface. Well, in that case, you can detect them together. But that requires a label or a tag for the biomolecule. You are not measuring the biomolecule itself, but the tag associated with it. Okay, this is something important to sort of remember. And if you see experimentally, this is indeed what is seen. I mean, this paper, for example, I took this data from this paper. You have two biomolecules. One is in here, shown in here, little one, and the another one is here. You can see how big this biomolecule is. This length is about a micron. So this size is something that is almost comparable. It would be a fraction of a micron. So this can be very, very substantial. And of course, the most sensitivity will happen when the biomolecule is in here towards the end compared to closer to the base. And you can indeed see that there is a shift in frequency. The shift in frequency, it is originally as 1.27 megahertz, and then eventually it is at 1.21 megahertz. So 0.06 megahertz, about 60 kilohertz shift in frequency. You can see still it can be detected, but if you try to go farther down, like 1 kilohertz or so, then it's not so easy. Now, if you could somehow improve the noise of such a system, then of course you could, in principle, you can even detect a single DNA base pair. Let me show you what might be possible. All right, so let's assume that you want to measure even something smaller. How small can you go? So here is an example. So for example, here, instead of using the classical cantilever, which has about 1.5 micron width, let's use a DNA, the carbon nanotube. Carbon nanotube only has 2 nanometer diameter, right? W has sort of effectively gotten very, very small. Thickness, previous case, 25 nanometer. Here, let's say we make it 2 nanometer. Again, it's a cylinder, right? So in that case, it is a considerably smaller cantilever. And in that case, we may be able to measure something that we couldn't measure even with this silicon-based cantilever. So this diameter is 2 nanometer. Let's say the length is about 2 micron, very similar to the silicon cantilever. Now, carbon nanotube has very large Young's modulus, 1 terapascal. And then, now one important thing is to remember that when you look at the mass of a carbon nanotube, right, people generally specify it as a linear density. So you don't have a rho. Rho is weight per volume, kilogram per meter cube, let's say. But here, often it's specified in terms of weight per unit length, integrated over the cross section. So here, for example, it is 5 times 10 to the power minus 15 kg per meter. It's very lightweight. All right. And the alpha 2 and alpha 1, all these values are given. And let's say somehow you have very high signal processing capability that can detect 500 hertz shift in the frequency, let's say. Now, of course, how would you do it? We'll discuss it later in the selectivity lectures, that you can actually average over signal and noise for a certain duration, take many samples, and in that case, one can, in principle, improve the signal to noise ratio so that even a smaller shift becomes visible. So, in the solution, this is fully discussed. Remember, single biomolecule. So we don't have a delta K term. Delta K term is gone. This is a cylindrical type of sensor, not a rectangular cross section. So therefore, your eye is slightly different. And then correspondingly, your mass is simply the linear mass density multiplied by L. So you put them together, calculate the change in the delta F. The bottom line is you get about a kilohertz change. Now, this is simply for a DNA of having, let's see, there is 4 base pair, assume, A, G, C, T. So there are 4 base pairs. So each one of them has about, the total is about 1230 Daltons. Dalton is, you multiply with mass of a proton. And in that case, it looks like that it is detectable. But of course, you have to do signal averaging. You have to have a DNA biosensor, carbon nanotube based biosensors. But you can see the ultimate limit, that even a small, tiny segment of DNA may become visible if you have if you can fabricate a DNA based cantilever sensor. Okay. Now, often, we have worked with analytical results. I changed everything so that you can, we can analyze everything in terms of spring mass system. But in that case, we need to know the alpha 1 and alpha 2. You know, that doesn't change the results fundamentally, the values of alpha 1 and alpha 2. Order of magnitude is always correct. But if you needed a full simulation, you can quickly do it by this additional simulator called MEMSLab. The MEMSLab, you can solve the same problem. And what you will see that you can add the mass. Before adding the mass, you apply a pulse, and then there is this resonance. Let's say the resonance is 7.41 megahertz for this particular problem. And then you add the mass wherever you want. And then the mass, after the mass has been added, the frequency has gone down. Remember, the delta M effect is always negative, 7.16 megahertz, about 300 kilohertz or so change. So you can do these simulators if you want more sort of quantitative answer. But other than that, these qualitative answers that we discussed previously, most of the time will get you the right ballpark. Now, one final thing I wanted to mention about this cantilever-based biosensor is that there are this new version, right? It's called a FlexureFET. And the FlexureFET essentially combines the biosensing associated with the simple cantilever and puts an electrostatics interaction so that the cantilever bends to a point where its sensitivity is much higher. And the key to enhanced sensitivity is the reduced K, or the reduced spring constant. And so this particular homework looks into that. One thing is that this y over y naught, you should not go beyond that 1/3 of a distance. So this is something I want to explain to you. Y over y naught, there's a critical value. I want to show you where that comes from. So you may remember that this is something we did in the class. If you have this green beam being pulled by this pink bottom electrode, then what happens that for every voltage you apply, it generally goes down, oscillates and stops at a point. And then if you keep doing it around about 20 volts for this particular example, then it will snap and snap shut. So for all biosensing applications, we have to sort of stay below this voltage. In this particular case, 20 volts. But you can calculate for every cantilever, it will be slightly different voltage called the pull-in voltage. We have to stay below it. And you can see at the transition point, this top side is 1/3 and this bottom side is about 2/3. So we cannot pull it below 1/3 because, cannot more than 1/3 because then we'll be pulled in and then we don't have a electrostatic, we don't have a sensor. So in order to get this analysis right, what has to be done is that at every point we have to balance the spring force associated with the spring. Spring is trying to pull it in the opposite direction and electrostatic force is trying to pull it downward. And so we have to solve these two forces and the solution will give us the steady state position. But the only point I want to make, and this is something we have discussed, the only point I want to make is that this critical point where beyond which you cannot, it is snapshot, requires two conditions. And this is something often in the beginning people miss. The first condition is the force has to be equal. That's fine. That's this curve and the rate curve, there has to be a solution. But at the point of transition, the slope, the tangent of the curve, the slope of this curve also has to be equal to each other. And if you do that, only then, with this additional condition, you will get the critical point. So let me show you how it works. So for example, this is the balancing between the spring force and the electrostatic force. So you can see that this is a cubic equation. That's fine. That's from the force balance. But the tangent requirement that the tangent is equal requires that we take a derivative of this, which gives you k, and derivative of this, which gives you minus y cubed. And so these two are equal. That's why the minus are gone. So you have k is equal to epsilon over y cubed v squared. Now these two equations have to be solved simultaneously. How do you do that? Well, what is done is that you can take this one y from here, put it up there. So you have epsilon naught a over y square v square. And that you can replace it in here. So that this will become ky for this whole thing. And once you put it in, the k will cancel, k will go away, and you will have a relationship like this. Otherwise, if you try to put cross multiply and then solve, that makes things a little complicated. And by solving this, you will see that the pull-in point is 2/3 y naught. And once you have the 2/3 y naught, then now you can essentially put this value in both cases, and correspondingly find out the pull-in voltage. Okay, so this is something you should work out, but I just wanted to emphasize that there is this little trick that makes your life a little easy. Now, one thing about this curve that I wanted to say, that the spring, remember this weakening of the spring is the key thing that we are trying to explore in this homework. And the final formula is the effective spring constant goes as 3 minus 2 y naught over y. The whole thing is multiplied by the k. Now, as you are pulling things down, the y is less than y naught. And so therefore, the whole thing is gradually becoming larger and larger until it becomes equal to 3. So for example, let's say this original gap is y naught without applying a voltage. And the new gap is y. Now 2/3 y is still here, but let's say a certain value is y. And so for example, if the y is 0.9 y naught, so it's just pulled down a little bit, 0.1 y naught. In that case, it's still 77% of the original spring constant. So that would be somewhere here, 77% of this original spring constant. But if you change it a little bit, let's say to 0.8. So this is 0.2, this is 0.8. In that case, the spring constant value is half of the original value. Increase it a little bit, let's say 0.7, it will immediately, strongly and very quickly drop towards 0. So what we really want is that we want to sort of operate somewhere close to here. If you are operating with a little bit of bias in here, then you will not get significant enhancement in the sensitivity. So therefore, working out this example tells you how close to the pull-in point you have to bias. Of course, if you are too close, then you can be pulled in. So you don't want to be exactly at 2/3 y naught. A little bit in the back, that should be good. So this is the purpose of this design. But example will help you decide at what point to bias this particular flexure fit. So that's about it. That's the homework that I wanted to know, are the homeworks that I wish to discuss this week. And we'll end here. Okay, thank you.